let's maybe start with something that it always blows my mind. You take our sun, right? This huge thing.
Yeah, enormous.
And you shrink it down. Imagine it's just like one single grain of sand.
Okay, got it. Tiny.
Well, that one tiny grain, that's just one star. And there are over, what, 200 billion stars in our galaxy, the Milky Way?
It's already staggering.
But then picture a beach, like all the sand on Earth.
Mm-hmm.
Some say there are more stars in the universe than grains of sand on all the world's beaches combined.
That comparison really puts it into perspective. The sheer scale is, mind-blowing is the right word.
And what gets me, really, is not just how big it is, but how we stuck here on this little rock.
Orbiting one of those grains of sand.
Exactly. How we managed to figure any of this out, it feels like this incredible human achievement.
It really is when you think about our limitations or viewpoint. It's remarkable.
Yeah, it all comes back to that basic question, the one you ask as a kid looking up at the sky. I remember growing up in Baghdad, sleeping on the roof in summer.
Oh, wow. Must have been amazing skies.
Incredible. And I just lie there looking up thinking, what is all this? Does it just go on forever? Or is there like an edge somewhere?
That fundamental question, it's driven so much of this journey, hasn't it? For centuries, the answer seemed, simpler.
Right. Earth in the middle, stars stuck at a big ball around us.
Pretty much. The geocentric model. Makes sense from down here, looking up. Everything seems to wheel around us, a celestial snow globe almost.
Seemed logical. But then 1572, something happened. Something bright.
The supernova. Tycho's supernova, sometimes called. A Type 1a. Basically a star exploding.
Exploding is putting it mildly. This thing was like 5 billion times brighter than our sun, suddenly appearing in the night sky.
Imagine seeing that. Must have been unbelievable. Shocking even. It was brighter than Venus, visible during the day.
People freaked out, right? Thought it was, the Star of Bethlehem returning or something.
Well, yeah, religious interpretations were common, but scientifically it started to poke holes in that neat celestial sphere idea. Well, take Thomas Digges, an English MP, actually. He was fascinated by it. And his friend, John Dee.
The famous alchemist.
That's the one. Dee had this idea, turned out to be wrong, but he thought maybe this new star was moving. Getting brighter as it came closer, dimmer as it went away.
Okay, so Dee was wrong about the moving part, but
it got Digges thinking, if a star could move like that, maybe they weren't all fixed permanently onto this, solid shell.
Okay. It undermines the fixed part of the fixed stars.
Precisely. Took him a few years, but then he published something, not a big paper, just a diagram, actually.
Okay.
Yeah, in his English translation of Copernicus's book, Copernicus put the sun in the center, planets orbiting.
Right, heliocentric.
And then he still had that outer sphere of fixed stars, Stellarum Fixarum. But Digges, in his version, he took those stars.
And did what?
Scattered them. Just scattered them outwards into infinite space. No shell. Just stars everywhere, forever.
Whoa. So no boundary, just
Wow.
endless stars.
That was the implication. A huge shift from this cozy, bounded universe to potentially infinite space. First time really in European thought, arguably.
Okay, but wait. If there are infinite stars scattered infinitely, wouldn't that mean...
You're getting there. The paradox.
Why isn't the whole sky just blindingly bright? If you look in any direction, shouldn't your line of sight eventually hit a star?
Exactly. That's Olbers' paradox, named after Heinrich Olbers, though Digges sort of hinted at it too. If the universe is infinite, static, and full of stars forever.
The night sky should be as bright as the sun.
Yeah.
But it's dark, obviously.
Obviously dark. Such a simple observation, but it pointed to a massive flaw in that infinite static picture, and figuring out why it's dark took, centuries, and some big new ideas.
So the puzzle deepens. Where do we go next to try and map this thing out?
Well, fast forward to the late 18th century, William and Caroline Herschel, brother and sister.
Herschel? Didn't he discover a planet?
He did, Uranus. But his story is amazing. He started as a musician.
A musician. Turned astronomer.
Yep. Totally obsessed. Started building his own telescopes, not just buying them, building them, better ones.
Oh.
He used metal mirrors, like Newton suggested, not glass lenses, could gather way more light. He even had a workshop in his house, melting down metals. Apparently it was pretty dangerous stuff.
Wow, dedication.
Total dedication.
Yeah.
And Carolyn worked right alongside him, night after night, scanning the sky, cataloging everything they saw.
And finding Uranus got him noticed.
Big time. Became king's astronomer, got funding, which let him tackle an even bigger project, mapping all the stars to get a picture of, everything.
Did he manage it? Does he see the edge?
He thought he did, kind of. In 1785, he published this map of the Milky Way, showed it as this big flat disk of stars, like a grindstone.
And us?
We were sort of near the middle, according to his map. It looked like he'd seen the boundaries of our star system.
But there was other stuff out there, right? Fuzzy patches?
Exactly. Nebulae, these hazy things, some look like spirals, some just like clouds, and that led to a really wild idea for the time.
Which?
What if? What if some of those nebulae weren't inside our Milky Way disk at all? What if they were? Other Milky Ways. Other island universes. Millions of stars each, but incredibly far away.
Island universes, I like that. But how could they tell? How do you measure distance to a fuzzy patch?
That was the killer problem. They just couldn't measure distances that vast. Herschel's telescopes were amazing, but they needed a cosmic yardstick.
So how do we get one?
Well, after Herschel, a technique called stellar parallax was figured out. It's like holding your finger out.
Oh yeah, I'm blinking one eye then the other. Your finger seems to jump against the background.
Exactly that. As the Earth orbits the Sun, nearby stars seem to shift slightly against the really distant background stars. Measure that tiny shift.
And you can calculate the distance. Trigonometry, basically.
Right. They managed to measure the distance to stars like 61 Cygni, found it was like 100 trillion kilometers away. Mind-boggling.
But still, only for nearby stars, right?
Yeah, that's the catch. The baseline Earth's orbit, about 300 million kilometers across, it's just not wide enough for really distant things. The shift is too tiny to measure accurately.
So parallax could reach out, what, 300 trillion kilometers maybe?
Something like that. A decent chunk of our local neighborhood in the Milky Way, but nowhere near far enough to settle the question about those nebulae.
So the mystery continued. Were they inside our galaxy or separate island universes?
Yep. Became known as the Great Debate in the early 20th century. Big arguments, passionate astronomers on both sides, and it stayed unresolved until someone found a new yardstick.
Okay, who cracked it?
Henrietta Leavitt, working at Harvard College Observatory. Her job, on paper, sounded kind of tedious.
What was it?
Counting and cataloging stars on photographic plates. These glass plates with images from telescopes all over the world. Meticulous work.
But she found something in all that data.
She did. Incredibly observant woman. She focused on a particular type of star Cepheid variables.
Variable, meaning they change brightness.
Exactly. They pulsate, get brighter, get dimmer, brighter, dimmer, on a really regular cycle, like a cosmic heartbeat.
Okay.
So Leavitt discovered something amazing. The speed of that pulsation, the period, is directly linked to the star's true brightness, its intrinsic luminosity.
Wait, really? So if you know how fast it blinks?
You know how bright it actually is. Think of it like two light bulbs blinking at the same rate. You know they have the same wattage, same real brightness.
Right.
But if one looks much dimmer to you...
It must be much further away.
Bingo. You compare its apparent brightness, how bright it looks from Earth, with its true brightness, which you know from its pulsation period, and boom, you can calculate the distance.
That's genius. A standard candle.
Pretty much. It gave astronomers a way to measure distances far, far beyond what parallax could manage, even though Leavitt herself, as a woman back then, wasn't allowed to actually use the big telescopes.
That's infuriating.
It is, but her discovery gave others the tool they needed to finally measure the distances to those mysterious nebulae. The island universe debate was about to be settled.
Enter Edwin Hubble.
Enter Edwin Hubble, yeah. Quite the character, apparently. Unlike the meticulous, quiet Leavitt, Hubble was, well, larger than life. Bit of an ego, maybe.
Huh. Tell me more.
Apparently spent time in England, came back talking with this exaggerated British accent, very theatrical, they say, but also brilliant, and he had access to the brand new, most powerful telescope in the world at the time.
The Hooker telescope.
At Mount Wilson Observatory, yeah. So Hubble had the best telescope, and he had Leavitt's Cepheid method, the perfect combination.
So what did he do?
He pointed that huge telescope at the Andromeda Nebula, the biggest, brightest nebula, and in 1923, he found one.
Found what?
A Cepheid variable star, inside Andromeda.
No way. So he could measure its pulse.
Measure its period, figure out its true brightness, compare it to how dim it looked.
And calculate the distance. What was it?
Immense. Millions of light years. Absolutely proving Andromeda wasn't just some gas cloud in the Milky Way, it was.
An island universe. Another galaxy entirely.
Just like ours, but unbelievably far away. We now know it's about 2.5 million light years. The light we see tonight left Andromeda before Homo sapiens even existed.
That just, wow. So in basically 1 year, 1923 to 1924, our whole picture of the universe just exploded outwards.
Exploded is right. From thinking the Milky Way might be it to realizing it's one of countless galaxies in this vast, vast cosmos, Hubble totally changed the scale.
But even then, he hadn't figured out the total size, right? Or the overall shape of everything.
No, not yet. His work pushed the boundaries out incredibly far, but understanding the universe's ultimate structure, its geometry, that required something else. Not just observation, but math.
Right. Observation tells you what's there, but math helps you build the framework to understand how it all fits together.
Exactly. And for 2,000 years, the math we used for space was Euclidean geometry.
The stuff we learn in school. Parallel lines never meet. Triangles add up to 180 degrees.
That's the one. Everyone just assumed that's how actual space worked. It seemed obvious, intuitive.
But it's not.
Well, mathematicians started wondering. Carl Friedrich Gauss, absolute genius, he suspected space might not be flat, might be curved. He even came up with this cool idea, his remarkable theorem.
What did it say?
Basically, that you could figure out if a surface is curved just by making measurements on the surface itself. You don't need to see it from the outside.
Like an ant on a balloon.
Perfect analogy. The ant, just crawling around, measuring angles and distances, could figure out it's on a sphere without ever leaving the surface.
Mind-bending.
And then Gauss's student, Riemann, took it even further. He generalized it to curved space in any dimension, including our 3 dimensions. He showed space itself could have shape, curvature, structure, without needing a 4th dimension to bend into.
Okay, my head hurts a little, but this was all just theoretical math. Did it connect to reality?
Not immediately. It was seen as brilliant mathematical exploration, but maybe not relevant to the real world until, well, you know who?
Let me guess. Einstein.
Albert Einstein. He took these weird, non-Euclidean geometries of Gauss and Riemann and said, wait a minute, maybe this is the actual geometry of the universe.
So space is curved.
According to Einstein's general theory of relativity, yes. Mass and energy actually warp the fabric of space-time around them.
Space-time, not just space.
Right. He showed space and time are interconnected, a 4-dimensional fabric.
Yeah.
And gravity. It's not really a force pulling things together like Newton thought.
It's not. Then what makes the apple fall?
It's the curvature of space-time caused by the Earth's mass. The Earth makes a sort of dip in space-time, and the apple is just following the straightest possible path through that curved space-time, which happens to lead downwards towards the Earth.
Whoa. Okay, so space isn't passive. It reacts to stuff in it. It bends.
It's dynamic, and when Einstein applied this theory, general relativity, to the entire universe, he got a huge surprise.
What happened?
The equations predicted the universe shouldn't be static. It should be either expanding or contracting.
Expanding. But didn't everyone assume it was just eternal and unchanging?
Pretty much. Einstein himself found the idea so weird, he actually fudged his own equations. He added this extra bit, the cosmological constant, to force the universe to be static.
Seriously? He didn't trust his own theory?
Not initially. He called it his biggest blunder later on, because someone else was about to find observational proof.
Hubble again.
Hubble again. He wasn't just measuring distances to galaxies, he was measuring their light spectra. And he noticed something consistent.
What?
Redshift. The light from distant galaxies was stretched out, shifted towards the red end of the spectrum, like the sound of an ambulance siren changing pitch as it moves away from you.
The Doppler effect, but for light. Meaning they're moving away from us.
Exactly. And crucially, he found the further away a galaxy was, the faster it was moving away, the more redshifted its light was.
So everything is moving away from everything else.
Well, the key insight is it's not just that the galaxies are flying through space, it's that space itself is expanding, carrying the galaxies along with it, like raisins in a rising loaf of bread.
So the space between the raisins stretches.
Precisely. And this observation matched Einstein's original equations perfectly, the ones he tried to ignore. Eventually, Einstein visited Hubble, looked through the telescope, and apparently admitted Hubble was right. The universe is expanding.
That's an amazing story. Theory and observation coming together.
Absolutely. And if the universe is expanding now...
You run the clock backwards. It must have been smaller, denser, hotter.
Keep going back. And you reach a point where everything was unimaginably hot and dense. A beginning.
The Big Bang.
The Big Bang. And we even have evidence for it, direct evidence. The cosmic microwave background.
The afterglow.
Yeah, the leftover heat from that incredibly hot early state. As the universe expanded over billions of years, that initial light got stretched and cooled down into microwaves, which we can detect today, filling all of space.
I heard like 1% of the static on an old TV is actually that.
It's true. A tiny fraction of that snow is the echo of the Big Bang. And by studying that CMB radiation really carefully, we figured out the age of the universe pretty accurately.
How old?
About 13.7 billion years.
Okay, so wait. If the universe is only 13.7 billion years old, does that solve the dark sky problem? Olber's paradox.
It does. It's one of the key pieces. The universe isn't infinitely old. So light from stars that are incredibly far away, further than 13.7 billion light years, simply hasn't had time to reach us yet.
So our view is limited. We can only see stars within our observable universe.
Exactly. The sphere around us, defined by the distance light, could travel in 13.7 billion years. And while there are tons of stars in that observable bubble, it's not infinite. Plus, the expansion itself redshifts and dims the light from distant galaxies. So there just isn't enough light reaching us from within that finite time frame to make the whole sky bright.
Wow. So the darkness of the night sky tells us the universe had a beginning.
Fundamentally, yes. It's amazing how that simple observation connects to such profound cosmology.
So where are we now? What does the universe look like on the grandest scale we can see?
Well, simulations based on galaxy surveys show this incredible structure. It's not random. Galaxies cluster together in these vast chains and sheets called filaments.
The cosmic web.
That's it, with huge, almost empty regions called voids in between. It's this gigantic, intricate network stretching across billions of light years. It would take light nearly 10 billion years just to cross the structures we've mapped.
Unbelievable. Have we figured it all out then?
Oh, not even close. Just when we thought we were getting a handle on it, another mystery popped up. Around 1998.
What happened?
Astronomers were trying to measure precisely how much the universe's expansion was slowing down due to gravity pulling everything back together.
Makes sense. Gravity should act like a brake.
That's what everyone thought, but the measurements showed the opposite. The expansion isn't slowing down, it's speeding up, accelerating.
Accelerating? How? What's pushing it?
We don't know. We call the mysterious cause dark energy. It seems to be some kind of energy inherent in space itself that acts like anti-gravity, pushing everything apart faster and faster. But what it is, that's probably the biggest puzzle in cosmology right now.
Dark energy, speeding things up. What does that mean for the future?
It's kind of a bleak picture, cosmically speaking. If it continues, galaxies beyond our local group will eventually recede from us so fast, faster than light can travel across the expanding space between us.
That their light will never reach us again.
Exactly. They'll disappear beyond our cosmic horizon. Our observable universe will effectively empty out over trillions of years. Future astronomers in the Milky Way might only see our own galaxy, maybe Andromeda, if it's merged with us by then.
And look out into a vast, dark void. They'd have no way of knowing about all the other galaxies that used to be visible.
They might conclude they are the entire universe. It's a sobering thought.
Definitely. From thinking we were the center to seeing billions of galaxies to maybe a future where we look alone again, it's quite a journey.
It really highlights how much our understanding depends on observation, on reasoning, on pushing the boundaries of what we can detect and comprehend.
Yeah, just remarkable that from this tiny planet we've been able to piece together so much of this immense story, the story of everything.
But as the accelerating expansion shows, there are still fundamental things we don't understand. What is this dark energy? What is space itself, really?
It brings you back to that basic question, doesn't it? Like, imagine a box, an absolutely empty box. You take everything out, atoms, light, everything. What's left in the box? Is it truly nothing? Or is the space itself something?
That's the deep question, isn't it? What is the vacuum? What is the nature of empty space? Maybe that's the next frontier in understanding everything and nothing.
A perfect place to leave people thinking. What exists when you take everything away? Wow.